This is my 17th video in my Casting Shadows series about shadows of ellipses, and please subscribe. When an object and its shadow are on parallel planes, the two are identical, and the shadow is displaced following the light direction, so all we need to know is distance d between them. This table casts an identical circle on the ground. We can find it by drawing light rays through its center and its sides. If we're looking at an ellipse from an angle like this chair seat, then we have to take into account perspective, where the shadow is slightly rounder than the seat because it's further from eye level. The most important line with circular forms is the tangent line that touches a curve at a single point. It separates the area receiving light from the area without light, so it's essential to shadow casting. Drawing tangent lines can sometimes be difficult, but one approach is to identify the tangent point, this red dot, and then find two green dots on either side equidistant to this red dot, and then connect the green dots together. Then you can find a line parallel to this green line that goes through the tangent point. When drawing a series of tangent lines like these, they get closer together toward one side as the curve gets steeper. When the light is tangent to the circle, the shadow disappears. You can see that with this wheel and its shadow, we don't see the shadow right here. In contrast, the center light ray goes through the widest part of the shadow. Here, the furthest part of the shadow from the center is along the central light ray. There are many ways of drawing ellipses, but one is to start with a true square and circle, draw their diagonals, and find points where the diagonals meet the circle, and continue those points horizontally until you get to the trapezoid, and then it proceeds to the vanishing point with the rest of the trapezoid. And where it crosses the diagonals for the trapezoid is a point on the ellipse. When you find an elliptical shadow of a circle, one way to do it is to start with a true square and then find the trapezoidal shadow for that square. And then fit in an ellipse so that it touches each side at one point, and it also touches the circle at one point. You'll end up with a slightly deformed ellipse, and the major and minor axes of this deformed ellipse is close to, but usually not the same as, the diagonals for the trapezoid. We could, of course, draw the ellipse freehand, but I recommend making sure you know where the major and minor axes are, because the tilt of the ellipse often is not what you expect. Alternatively, we can drop seats down from corners of the ellipse and use light triangles to find points on the shadow. For a vertical ellipse, the easiest method is to establish poles and then use light triangles to find intersections on the shadow. For this bicycle wheel, I found this to be the line between the bicycle wheel and its shadow, and the poles go down to this line, shadow line goes there, and it meets the light ray at points on the shadow. Alternatively, you could use what I'm calling the spokes method, where you find spokes on a wheel and then draw light rays from the end of each spoke to the shadow on the ground. And if you do enough of them, you will find shadows of the spokes that go through a point on the shadow. Turns out that you can use my spokes method for any ellipse, including the horizontal one I show here, and even a slanted one. So it becomes very useful when we do shadows of spheres. So in this first case, I drew the major and minor axes of the ellipse, and then I drew light rays from each end to find their shadows on the ground. And if you do enough spokes, then you will get the shape of this shadow. Now, in this case, I did the same thing, and notice that the ellipse is a little distorted. And despite that, this spokes method was able to accurately find this shadow. In this image, I put the wheel in a square, and I found the trapezoidal shadow for that square, finding these 2 points by light triangles. Then I put in an ellipse so that it touches each side at 1 point, and it touches the circle at 1 point. Now notice that the major and minor axes of this ellipse intersect about here, but you can see over here that this is the center of the shadow of the middle of the circle. And to find that, you could just use a light triangle and it would lie around here. In this image, we can pass light rays tangent to the point where the shadow disappears, and we can also draw a light ray through the center of the wheel where the distance between the wheel and its shadow is the greatest. The back wheel looks almost identical to its shadow, so its major axis parallels that of the shadow, which is right here. That's not the case in the front wheel, which is turned this way a bit. So its major axis is like this, and the major axis of the shadow is more like that. My next video is about shadows of spheres.